All right, so this is a continuation off of homework 2. We'll now be moving into part C of this assignment. Here, we're tasked with finding the distillate bottom flow and composition of a system that has a feed flow rate of 1 mole per second with a feed mole comp of 0.55. We know that's a saturated liquid, so we can identify that the Q value for that will be equal to 1. So we can start this by opening up Drive. Tab here. All right, and here we have a lot of the data that we were using for the previous homework. All right, so we have all the data that we used for the previous assignments for calculating the Rashford-Rice equation and generating plots for that. So now building off of that, we can input our conditions. So here we know that the feed flow rate is equal to 1 mole per second. So we can put F equal to 1 there. We know that C is equal to 0.55. What else? No. Distillate composition is equal to 95% or 95, so we can say 0.95 there. And we know that the distillate recovery of this system is 90% for the more volatile component. So we can say rec is equal to 0.9 here, and that'll help us with this assignment greatly. So all that we're given, and then yeah, then we're able to say Q is equal to 1. So you can say Q equal to 1 here. These are all of our parameters that were given here. So now you need to be able to solve for the distillate composition or for the distillate flow rate. So here we can utilize a typical mass balance on this distillation column. So we know that 1 mole per second of feed is going into that column with a feed composition of 0.55. And then we know that distillate composition as well. So using that, we can set the, so we can say that D times XD is equal to that feed flow rate times its composition. And here we're in the problem, we're given the crucial value here, which is the recovery. So this 0.9 here, that basically it states that the amount of distillate that we want to recover from the feed is 90%. So we can include that into our calculation for that distillate flow rate by saying that this mole balance is equal, the mole balance of the distillate going out is equal to the mole balance of the feed coming in times the recovery. So doing that, we can then divide by XD to get our distillate flow rate. So now we found the distillate flow rate. We can now calculate the bottom's flow rate by using a more generalized formula of the material balance. So we know that the feed going in, right, is equal to the bottoms plus the distillate going out. So if we just rearrange this equation to solve for the bottoms, we can say that the bottoms is equal to the feed minus the distillate. All right. So that's all. That's all for our bottoms flow rate. And for the final component that we need to calculate is the bottoms composition. So to do that, we can do something similar to what we did up here and say that the bottom's flow rate times its bottom's composition is equal to that inlet flow rate times our composition times 1 minus our recovery, because we know that whatever is being whatever of that 90% is being returned, that bottom 10% is being left as distillate because we're dealing with a binary mixture. So we can say that this bottom's flow rate times its composition is equal to the inlet flow rate times its composition of the more volatile component times 1 minus the recovery of the system. So once we do that, we can just simply divide by B here, and we're given the bottom's composition for this unit. So shift enter just to make sure everything looks right. Perfect. All right. So now that we have all this calculated, we can start working on the second part of this problem, which is tasking us to generate a McCabe-Thiele diagram and showing the results of this with more parameters given here. So here we can put in our relative volatility into our parameters. We'll call that alpha. We'll say that alpha is equal to, what's that, 2.5, right? 2.5. And then we'll be varying the reflux ratios, but for now we'll say that we have a reflux ratio R of 0.8. Okay. All right. And then another thing that we will want to add into this, just to ensure that we don't run into any errors when it comes to subtracting 1 from our value of Q. We want to put in here that EPS is equal to, what is this, fan info dot P float. Actually, hold on, let me check. All right, yeah. So that EPS value is equal to NP dot NP float 64. Well, 64 dot, yes, should. Nope, never mind. Oh wait, we forgot the. Oh. All right, so yeah, so now we have our EPS factor here that will allow us to bypass the error that we'll get when we subtract 1 from Q, or when we subtract, yeah, 1 from Q, or Q from 1. So now we can just build out our lines for this diagram. So here, we'll just copy and paste what we have here just to make life a bit easier on us. Just paste that right here. All right, just enter. All right, so we have our diagram here. We have our VLE diagram here. So now we can just we'll start by adding in the line for the rectifying section in this diagram. So first we'll say we start at XD. So here our starting point for this line will be at XD, right? And then for Y, that starting point will be XD as well. And then here, our ending point that will be when x gets to 0 here. So we'll say that x is 0. And then for y, we've already calculated what, or we already know what um, y will be when x is equal to 0 for the rectifying section. So I believe that is r divided by r plus 1 times xd. I believe. Let me put some parentheses on it just to make sure. Times xd. And that should be boom. All right, perfect. Yeah. So here we have our rectifying line here, as shown, and we can mess with this, or we can adjust this by messing with the reflex ratio, and we see how far off it deviates from this y equals x line here. So if we even put that as 0, follows the y equals x line right there. So that's our rectifying line. Now let's model in our Q line. Let's model in our Q line into this diagram. So here we start with our x. So our x will start at z. So here the starting point for this line will be at z here. And that will be the same for this y value here. So we start at z. And then here, when x is equal to 0, we just utilize utilize the equation that we derive for the q line in this, and um, evaluate what that value, or what that equation is when x is equal to 0. So I believe we wrote that down. Yeah. So that value becomes z1 minus q here. All right. So then once we do that, oh, and here we go. So this is kind of what I was talking about when we were deriving this EPS here. So we see here that because we're dealing with a saturated liquid, we know that our Q value will be equal to 1 here, signaling that we're at the bubble temperature, or that the feed is coming in at the bubble temperature, and that the feed is completely liquid. So here we need to be able to add a value that allows us to run this program without running into this error. So we just add EPS here. And another thing we'll have to do is have to add in our limits. So it's update x to fig update underscore x. Perfect. Then we set the range. Yep, just okay. Range. Copy that there. Boom, boom. Do the same thing for the Y's. Boom, boom. And bang. So now we've generated our Q line for this McKay-Daly plot. So now that we've done that, we can now generate the line for our stripping section. So follows the same pattern here, except this time for our starting x and y values, we're going to start with our bottom, or our bottoms composition. So we start with our bottoms composition there, xb, right? And then for the ending point, so we want to draw this line all the way up to the top. So that would be when y is equal to 1 here. So here we just change that to when y is equal to 1. and we derived, or did we derive? Yes, we did derive. So we derived what this equation is when y is equal to 1. Yeah. So we derived that in the earlier part of this video. So that was f minus q, right? D minus the distillate r plus 1. All right. Is divided by our bottom's flow. All right. Flow is not callable. The EPS there. So let's add the EPS and see if that object is not called. We have, so here we have, I found the problem to so I found the problem here. So I just forgot to multiply those out right there. And then here you can see that this line is not at all what we're expecting, and that's because we're using the wrong equation. So we're going to X all that out and put in the right equation that we did derive, that being when X is, so when Y is 1, X is equal to XB plus VB, which we have not calculated yet, but we can put that into divided by VB plus 1. So we do VB plus 1 there. All right. And that's what that is there. And then we just need to put in, what VB is because we haven't calculated that. Excuse me. We haven't calculated that yet. So if we look through, we know, so that was the equation that I put in earlier, that VB is equal to, looks like it had it there for a sec. VB is equal to, let's see if it, nope, that's not it. That is not it. No. So we have F times 1 minus Q there, and then we subtract D times R plus 1, and then we divide all that by our bottom's flow rate. So divide that, we all right. So I have some very crucial errors that I made in the code to address. First, being that I used the wrong equation for the stripping section part of it. Yeah, so here, this is what we get when y is equal to 1. This is the equation that we get for what x is. Here we plugged in that equation that I used previously into the to calculate the boil up ratio here. And one thing I did mess up on there was just switching the signs for these two variables. So it should be the distillate times our reflux plus one minus that feed times the or the times 1 minus q divided by v, or bottoms rate. Also used the wrong equation for the rectifying section. So I mistakenly put R here. So that wasn't correct. I need to look at the second part of the equation, which is 1 over R plus 1 times XD. And then another thing that I messed up on. Oh, where's that? Yeah, so for calculating the distillate flow, for some reason Python did not like that I used parentheses here. So, or I guess it doesn't matter. Never mind. So yeah, so those are the errors that I found in those calculations. Now we've built our McCabe-Thiele diagram. We have our intersecting points. We have our stripping line equation. We have our rectifying line equation, and we have our Q line equation. Now from this, we can calculate, or we can do the staircase for this to determine how many steps are necessary for this calculation. So we do that by creating a for loop. So first we'll uh, define our variables here. We'll say x underscore staircase here, and we know that that starting value, since we know we're starting at the top here where the distillate value is, we can set that value to be equal to our distillate composition. So here we set that as xd, and for y we do the same, y staircase. We set that as xd as well. And then our starting value for y will actually be xd. And then from there we can utilize the for loop to change that value, or to add on new values. So we'll say for I in range 100, I believe. Okay. So here we can utilize all right. So first what we have to do is we have to define what our starting x value is. So as of right now, we know what xd is, and by knowing that, we are able to translate what y1 would be. Now the problem is we don't know what x1 would be. So we need to be able to formulate an equation to figure out what that is. And we can do that with the equation we utilize to find the vapor mole fraction given a liquid mole fraction and our alpha term, 2.5. This time we'll just be doing that in reverse to find what that liquid mole fraction will be given our y mole fraction and our alpha term. So if we remind ourselves what equation we're talking about here. So we know that y is equal to alpha. Let's call this alpha here times x, right? And that's all divided by 1 minus x plus alpha times x, right? So we need to be able to reorient this equation to solve for x here. And when we do that, we're left with the equation that x is equal to y divided by alpha plus y minus y times alpha. All right. So this gets us our x1 value and the preceding x values to come in this loop. So there we're able to calculate that x, and then we can just append, or we can do X staircase, stop append, let's append X there. And we can do the same thing for Y. So staircase dot append Y. All right. So that's the first part of this loop. Now, we want to, so now for the rest of this loop, we want to be able to create a way so that we don't end up taking too many steps off of our theoretical lines. So what I'm trying to say here is, so we have our bottoms composition and we have our distillate composition. So we know that we were given this distillate composition 0.95. This is just something that we chose to use for this calculation, or something that we want to theoretically achieve in our distillation column. However, in reality, we wouldn't really be able to set this distillation column because we need to make sure that this diagram is directly correlated with our bottoms composition to ensure that we're not over theorizing how much distillate we can get from the system. Because if we have this set value of a distillate that we want to achieve, but our McCabe-Dealey diagram is going, the steps taken are going way off from our distillate or from our bottoms composition, then it's just not possible. So we want to be able to set everything from this bottoms composition. So how we can translate that into the loop is, say, if X, all right, is less than XB, right, we break the loop. We just completely break the loop. All right. Else, so else, then we just utilize. So first, we want to draw the staircase for the operating, or for the rectifying line. So we want to draw that staircase for the rectifying line. So to do that, we just utilize the equation that we derived for the rectifying line. So we can say that y is equal to r divided by r plus 1, r plus 1, right? And then that's all multiplied by x, so times x, times x, right? Add xd divided by r plus 1 here, right? So that gives us the equation for the rectifying line. And then we need an equation for the stripping line, for the stripping section of this line, or of this diagram. So we can say that we can just input our stripping section equation here. So we have VB plus 1 over VB. That's all multiplied by x here. And then we should just subtract xb divided by vb from that. And from that, we can then append that staircase to x and y staircase, just like that. Steve should enter, see if this works. Syntax, maybe I'm supposed to put those there. So it's missing a bit here. So we need to, so now we've set this condition to make it so that our x value doesn't exceed our bottoms composition. we now need a way to differentiate between whether we're taking steps in the operating line, excuse me, or if we're taking steps in the stripping section. So to do that, we can utilize one of the equations that we built out earlier in the video, and we can make a new variable. Let's call this, well, let's call this x-intercept. X-intercept, right? And that is equal to the two equations that we set equal to each other to represent the intersection between the stripping section and the rectifying section. So that equation was, yeah. So we know that that is equal to 1 divided by r plus 1 around here. 1 divided by r plus 1 times add xb. So xb divided by vb, that all divided by plus 1 is minus r over r plus 1. And that gets us our x-intercept. So now here we can say if x is this, so this will be greater than, if this is greater than our x-intercept, utilize that. All right, yeah. So now we've built out our loop to generate our steps. So now we can just add those steps into the graph. So here we'll Control C, and then we'll Control V. We'll say that, so here we'll say that our x, that's just our x intercept, or no, not x intercept. This is our x staircase, and then y, that will be our y staircase modes, and then we'll change the color of this to green, just to show the difference. So green, we do that, and starts at XD, correct? And okay, hold on. All right, so went back into the code and found some other mistakes. So here I had fat fingered and just forgot to add the I here. So it was just wasn't getting the value that I was supposed to be getting. So I added the I there, and we were able to get this graph. However, something I had noticed was I had accidentally forgot to put the D here for XD. So I was just putting X here, and you can see here the steps were not following the operating line, or for the operating line for the rectifying section. So it just added B there, and then we were able to get this beautiful plot of our McCabe-Thiele diagram showcasing the steps and the amount of trays needed in this distillation column to get said 0.95 distillate purity. So next what we'll do is just mess around with this reflux ratio to see how many trays we'll need to have for this column. So for R, we can say R is equal to 0.8 here. And you see here we get real crunched up on that equilibrium line to the point where we can't even we're not even able to realistically get that level of purity here. Something I do want to check is my Q line. That is all right. So, after relooking at the code, um, I was able to somewhat figure out what was happening. I believe there was some error being associated with me putting parentheses around this term. I'm not too sure why Python was so sensitive to that. But now basically we can test out the varying reflux ratios. So here we have zero point 0.8. It's not right at all. Okay, let's try this. Oh, okay. So now we can see um here that that gets us very close to the equilibrium line to where we wouldn't be able to achieve that distillate composition. Next, we can try 1.5. So here we could try 1.5, um, and so no parentheses here, I guess. Yeah, we can see that they intersect, and we have more trays to utilize to get to that desired distillation or distillate comp. So now if we try 5, so we just put 5 here. Um, so yeah, we can see that it takes less trays to get to that desired distillation point if we run more reflux through it. So this concludes homework 2, and we basically derived the McCabe-Thiele plot, derived the governing equations behind that graph, and are able to see how many stages / trays we'll need for a ideal binary mixture.